Chapter 7 of our textbook covers the power series method. Here's an overview. This is the general structure of a linear ordinary differential equation with variable coefficients. In general, we assume all coefficient functions a0, a1, a2, and so on are continuous, and so is f of t, the non-homogeneous part. Why continuity, by the way? Because continuity allows us to use the fundamental theorem of calculus, which associates a definite integral with antiderivatives. Here, the continuity is not enough because we want to use power series, not just integration. So power series must be valid. That kind of function is called analytic. The kind of function where power series expansions are valid. Now, what is a power series expansion and what did you learn about power series in Calculus 2? Let's do some review. But if you already feel comfortable about Calculus 2 and you're anxious to go over to the real thing, skip this video from this point on and go to the next video. Otherwise, stay here for a review. Here we go. This kind of thing is called a power series expansion or Taylor series expansion. More precisely speaking, Taylor series theorem, by the way, is a computational formula to find out the coefficient using the repeated differentiation. But let's not go in there too deeply. Let's have as brief a review as possible. Whenever you have power series expansion, think about this ratio test. Yes, you can use root test as well, but ratio test is more useful. It's slightly less powerful, but heck of a lot easier. And ratio series theorem goes like this. Let me expand the font. Let L be the limit of the ratio of the two consecutive terms. And the limit is less than 1, then we have to have absolute convergence. Greater than 1, then we have to have divergence. That's the ratio test theorem. Now let's look at this limit a little bit more carefully here. So we want this limit to be less than 1 for absolute convergence, right? But let's do some algebra. This nth power part and n plus first power part cancel each other out. And then we just have one power here. Once you do that, then I don't have expression of n here anymore. So I can take this one completely outside of this limit, like this, times absolute value of that. And we don't need this parenthesis anymore. Now let's do some further algebra. This part here is less than 1 over, and then we can flip this limit computation to the other side. So we got the same condition as before. One more thing, please. Too many fractions. So what I'd like to do is flip over this fraction like this. Consequently, we have Cn over Cn plus 1. And this condition here is equivalent to L is less than 1. So this condition here is for absolute convergence, as a matter of fact. This computation yields the next result here, the radius of convergence. This thing over here is named as R, and that's called the radius of convergence. Why is this called the radius of convergence? Well, you can see it like this. What do you mean by this? Which is equivalent to that? Well, you can rewrite it like this. T0 minus R is less than T, but T is still less than T0 plus R. Now, this one over here, which I'm highlighting in red, and this part over here is equivalent to this thing over here, which I'm highlighting in red. All these are associated, of course, to absolute convergence. After all, this red, and that red are all equivalent. Please remember, L is this limit computation, R is that limit computation. And that concept yields the interval of convergence, as we see down here. What is this? That's equivalent to T belong to this open interval, which I'm highlighting in red. Okay, I don't need this anymore. So they're all the conditions for absolute convergence, written a little bit differently. And that's why this thing is called interval of convergence, because outside we have divergence. And then T0 is the center of the interval, so this capital R is called the radius of convergence. Now for one-dimensional case, which is for real analysis, we have an interval, but if you go over to two-dimension complex numbers, in that case you really have a circle and you really have a radius. Now, what other things do you have inside the interval of convergence? Next topic, let's look at the term-by-term differentiation. We can take the derivative each term at a time and then add them later on. That is not always true, but within the interval of convergence, it is true. Difficult to prove, but let's just accept it as is, as we have done it in Calculus 2. Same goes for term-by-term integration, which is a little bit easier to prove, but still, we are not going to do that here either. Please note that we simply took the antiderivative of each term, one at a time. By the way, proof of all these, well, we went through the preliminary version of those proofs in Calc 2, but it will be completed in Real Analysis 1 or 2. Here in this class, we'll just accept them and use them. Let's go over to the next topic, some well-known power series. Here is an expansion formula for e to the t power exponential function. And this is for cosine function. Please note that we have all the even terms, even powers, excuse me, and sine function, or the odd powers, odd terms. This is just a geometric series formula, and upon taking the antiderivative with some sign change and so on, we can find out the Taylor series expansion for log functions. These are some well-known examples of power series. There are more, but I think these are sufficient for our class. Next topic, index shifting. Let's discuss it in a next video.